Hi there. Well, since you're back, that means you've attempted to solve this fairly simple problem using Malus's law. Let's see if you got the right answer. Here was the question. We have a 100% polarized beam of light. It comes into a polarizing filter, which is tilted with its transmission axis 45 degrees away from the polarization angle, and that is theta is 45 degrees. If you figured that out, you're going to know what the answer is, because the cosine of theta is square root of 2 over 2, and so cosine squared, which is what Malus requires you to do, has got to be a half. Yes, that's right. The emerging intensity will be half of the original intensity, and interestingly, it's now purely polarized also at a different polarization angle from what it came in with. It's been, in effect, if you want to say this, rotated by 45 degrees. That was pretty neat. Not totally obvious, actually, but that's what Malus' law says, and that's correct. Let's do some slightly similar problems. These are very similar to MCAT type questions, warm-up questions that might appear on an exam, for example, in Physics 6C also. And we've got multiple choice questions here, but this covers just about every possible conceivable answer. Now, you got to read the question carefully. That's really half of the problem here, as you all know. I've got two problems which have the same two polarizing filters and pretty much the same set of answers, but I'm just going to change one little detail here about the starting conditions. In this problem, we have incident light which is unpolarized. Put that in italics there. So unpolarized natural light comes in to a filter, and the filter happens to be transmission angle at theta 1 away from vertical here. Then it's obviously going to acquire some polarization passing through. Then the polarized light that transmits from the first filter hits the second polarizing filter, which is tilted a different amount in general. Theta 2 is the angle of the transmission axis of the second filter. So what's going to happen next then? The transmitted light that finally emerges is going to be what? It's one of these six answers here. Obviously, it's proportional to the initial intensity I0 that comes in, and then there's probably going to be some cosine squared terms in here. So for these kind of problems, and this is like the first non-trivial problem we've got here, you have to realize that every time a Polaroid filter comes along, it's multiplicative. Its effects are multiplied by the light that's fed into it. That's what Malus's formula says. And so now that we have two Polaroids back to back here, the Malus's formula is going to have to be used multiplicatively. The output intensity from this filter then becomes the input intensity for this filter. So we just multiply. If I had three filters, that would be fancy. We'll see that in a second. Then I'm going to have to multiply three transmission factors from Malus. Well, let's see. So by the time that the light passes through the first filter, remember, and this problem is unpolarized to start with, what's in its intensity if it was originally I0 on this side? By the time it goes through, what's the intensity? Well, we already did that one. It's simple. It's just I0 over 2. So immediately I'm not interested in these answers on the left side because they don't have I0 over 2. It's 2, 4, 6 possible answers. So we send I0 over 2 through this filter. But now notice the difference. This time the light is entirely 100% polarized which way? It's polarized along the theta 1 direction. Is that the same as the transmission axis of this Polaroid? No, not in general. This Polaroid is a different transmission axis, and remember, the Malus formula only cares about the difference in the angle. It cares about the difference between theta 1 and theta 2. So we have feeding into this I0 over 2, and then Malus's law says there should be a cosine squared of the angle difference between the polarization in and the transmission axis of the filter. So that's theta 1 minus theta 2. So I've got to look for something here that has a cosine squared of theta 1 minus theta 2. Only two possible answers could be 4 and 6. 6, sorry, that's getting a little bit too carried away there. That is not right because there's no reason to depend on theta 1 initially. Who cares what theta 1 is initially? It's unpolarized natural light. So theta 1 could be anything initially. So you can see then Malus's formula here gives you the correct answer, number 4. Number 4 is the correct answer to this problem. Now I'm going to give you exactly the same problem, except I'm going to put polarized light in at the start. The incident light is going to be polarized at, let's see if I can get it to go. It's going to be polarized along the vertical or z-axis here. That's the only difference. Polarized, italicized, vertically, z-axis. Well, is that going to change anything? The intensity is still I naught. Let's see. Yes, it might change something. The change is going to happen going through the first filter, because now we've got to pull out Malus's law for a pure polarized beam coming in. And what does that say? The intensity passing through this Polaroid is going to be I naught times what? Times cosine of squared of the angle between the polarization that comes in and the transmission axis. There's the transmission axis of the Polaroid. So we now expect that we do need a cosine squared theta 1 in here. It now is going to make a difference because we have to know how far the transmission is rotated off of the input polarization. Then it passes through the next filter, and that factor gives us the same cosine squared of theta 1 minus 2 that we had, theta 1 minus theta 2 we had in the previous problem. So I still want either answer 4, 6, or 5 here. Let's see. Which one? Is there going to be a half anymore? Sorry, no, that was just an average for unpolarized light coming in. That was the previous problem where we wanted a half. Now I do not want a half, but we have to take into account that the previous light was polarized, and so depending on how large theta 1 is, we might have lost quite a lot of the incident light. Started out I naught, it's going to go through the first filter, and in between here, it's going to be I naught cosine squared theta 1. Aha! So the only formula that has the first filter, I naught cosine squared theta 1, and then the effects of the second filter, cosine squared theta 1 minus theta 2, is your correct answer down here, number 5. Number 5, the correct answer in the problem 2. You see just a subtle little bit of difference about the inputs. Reading carefully makes a significant difference in the result. Now here's a fun one, kind of qualitative, maybe. We're going with straight Malus's law here because we're putting in a vertically pure polarized beam. That's your incident beam, and the first step is going to be the same in all 3 cases. Well, duh, that seems pretty obvious. This is basically the one that you did at the break here. We pass through a filter which is rotated 45 degrees away from the input polarization. So theta in Malus's law is 45 degrees. Cosine of 45, 1 over the square root of 2. Cosine squared of 45, 1/2. So in all 3 cases, the light here is 1/2 of the initial intensity, 1/2 of the initial intensity, 1/2 of the initial intensity. Let's assume that the beams are input intensity is the same in all cases. So everybody is the same here, down to half of the light in here. Now that light is polarized slightly differently now. Now it's polarized at a 45-degree angle because that was the transmission axis that it just came through the first filter. It sets it up for the second filter. So now we only care about how far the transmission axis of the second filter is away from 45. Well, all of them, it turns out, are away from 45. Let's see how much. This one is 90 degrees, so it's 45 degrees more than this one. So theta 1 minus theta 2 is 45 degrees here. That's the difference angle. And so we're going to suffer another factor going through this Polaroid, again, of cosine squared of 45 degrees, again. So this filter knocked off half the light. Then coming through here, this Polaroid also knocks off half the light. We've got how much coming out here? 1/2 times a half. We have only 25%, 1/4 of our original light surviving this setup. How about this case right here? Does it really make any difference, by the way, whether theta is plus 45 or minus 45? Does that make any difference? Well, look at cosine theta. Look at cosine theta squared. It turns out it doesn't make any difference whether theta is replaced with minus theta. There's a symmetry there in nature. So this case is exactly a symmetric version of this case. In both case A and in case B, the second Polaroid was rotated 45 degrees. I don't care which way. It was 45 degrees away from the input polarization. Here it was plus 45, here it's minus 45. Same answer, same thing in both cases. Half the light comes through here, and then again another half of the light is absorbed. Only 25%, 1/4 of I naught gets through in case B. A, B, same case. So now I'm only interested in answer 3 or answer 5 because they both have 1/4 of the original intensity coming through at the end. Uh-oh, what about this one? Little deceptive here. The polarized light from the first transmission filter comes through 45 degrees away from the vertical, but it's tilted over here, looks like to the right here. This is 45 degrees too, but the transmission axis of this Polaroid in case C is rotated the other way. Got to think three-dimensionally here. You can see this in the drawing pretty well. So what's the combined difference? We only care about the combined difference between input angle and transmission angle. Well, it's 45 minus a minus 45. These two axes, this axis and this axis, differ by 90 degrees. Well, everybody knows what that case is. 90 degrees means that an ideal Polaroid blocks everything, won't transmit anything. So the intensity of any light passing through a configuration C is 0. What's the answer that's consistent here? It has to be answer 3. We get 1/4 of the light, 1/4 of the light, 0% of the light. So that's a nice kind of MCAT question too. I've used this on Physics 6e exams as well. Nothing too complicated here as long as you keep track of your angles. This is weird though. I got to show you this one. This is a little bit more about the angle that the polarized light ends up as it passes through a series of 3 filters. So this is probably one of the more complicated problems I want to show you, but it's just complicated enough to mess with your mind. And I like doing that a little bit, just a little bit here. And why does this mess with your mind? It looks pretty simple. What's the big deal here? All I'm going to do is pass unpolarized natural light through a filter, and you can see conveniently we have black lines going vertically here to indicate that could be the orientation of these Polaroid film molecules. This indicates that the transmission axis of this polarizer is vertical. No problem. So we already know that when the light passes through there, half of the light gets through with a purely 100% vertical polarization. No problemo. Now, we have another Polaroid. My gosh, is this the same as the last problem here? Hope you're not going to sleep. This is 45 degrees rotated away from vertical here, so we know exactly what's going to happen here. This arrow, by the way, is supposed to be half of the intensity of this one. All right, it says 1/2 I naught here. Now we pass polarized light through a filter that's 45 degrees off. We have cosine squared of 45, which is a half. We get 1/4 of the intensity of the polarized light, and of course now it has to be polarized along this 45 degree tilted angle. Then, this is the fun part, this is where things get interesting. We decide to pass it through, actually this was the same problem, wasn't it? Very similar to the previous problem. We pass this polarized light, polarized at 45 degrees, through a horizontal transmission axis Polaroid here. So again, there's a 45 degree change. The angle in Malus's formula is 45 degrees. Cosine squared of 45 is a half, so we take a fourth times a half. Only 1/8 of the light passes through. Hey, but that's not too bad. Now here's the thing that might surprise you about this. You may have in your mind a mental picture, which I must admit I have in my mind too, and we're going to have to ditch that mental picture here. My mental picture of electromagnetic light that's polarized vertically is that it's pure in some sense, and that it's the opposite of horizontally polarized light. Never the twain shall meet. That you could never do anything to take purely vertically polarized light and ever get horizontally polarized light. I mean, they're 90 degrees apart from each other. That's orthogonal. But that mental picture is not entirely true, actually. Look what happened here. We passed purely 100%, there's no trick, 100% purely vertically polarized light by just picking two kind of intermediate rotated Polaroids here. I ended up with a little bit of light. All right, it's not very much light, but it is still, a quarter of this amount of light, which was the orthogonal 90-degree different polarization. It's purely polarized in the horizontal direction. I seem to have extracted a little bit of horizontal polarization out of something that was purely vertical before. That's kind of weird. It's kind of an aspect of quantum mechanics. And here's what's really weird about it. You're always thinking of polarizing filters as gatekeepers, which will either stop you from going through or let some subset of the waves go through. Right? It's purely negative. So far, what we think about these filters doing. They never do anything positive. They either stop things from going through or let some of them grudgingly go through if they have exactly the right orientations. Not exactly the right, but nearly the right orientations. Wait a minute. What's the effect of this filter? What if we were to pull the middle filter out? And this is really weird. Take the middle filter out. And there's no middle filter. We just polarize the light vertically with the first filter, and we pass it directly, over to the horizontal filter, where you know darn well what comes through then. We have vertically polarized light. We slam it immediately without any preparation into a horizontal filter, and we get zero intensity. It's all wiped out, just as you would obviously expect. So this is the weirdness. Putting this extra filter in, this filter can only absorb. This filter does not produce light. I swear, it does not produce any light. It only absorbs light. This is weird. Putting a filter in between these two other filters, which can only absorb light, increases the signal that passes through the three-filter combination. When you slide this one in, the intensity that was 0 goes up to 1/8 of the original intensity. Putting this extra absorbing filter in allows light to pass through the filter combination. How weird is that? By the way, so weird. What if, just for fun, what if this last filter were purely vertically polarized? Would that make any difference in this problem? Well, if I didn't have the filter in the middle, we'd get all of the light half I naught coming through. But with the filter in the middle, we still have another 45-degree rotation, so we still get 1/8 I naught passing through, except we back in the original vertical polarization. So if you don't believe this, I must admit, I first saw this, I could kind of hardly believe it myself. So you have to see the demo where we actually take three filters, line them up like this, and see what happens when I pull the middle filter in or out, and by golly, it does work. That is so weird and so amazing. One last point here, which is how can natural light ever get polarized if you don't have Polaroids around, before those were invented? Well, there are some natural polarizers in the world. One of the greatest natural polarizers is reflection, especially reflection off of something, for example, something wet, something that conducts electricity. Whenever you reflect natural unpolarized light, like sunlight, that's supposed to be the sun there. Here we are at the beach. See all of the different E vectors coming down from the sun in all different directions, equally represented. They bounce off the flat surface at an angle of the water, and then only the sideways or horizontal polarizations are reflected. This is a very powerful polarizer, actually. And so in general, whenever you're looking around in any landscape, if you're not looking directly at sun, you're looking at reflections of sunlight. It is highly polarized, horizontal to the ground. That's called glare. You probably didn't want to see that. Maybe you're looking for something in the water there, something of interest perhaps. Then you don't want to be just looking at glare sunlight. That's irritating. And you would, for hundreds of years, people have been to the beach and said, gosh, I wish that I could have a filter that would block out just the glare of the sunlight. I'm not interested in that extraneous reflected polarized light. And that was really one of the big motivations for inventing mass-produced Polaroid filters in the first place, to make sunglasses. This poor guy doesn't have any sunglasses, can't see anything. Proof that this is a very powerful effect. I'm going to take a picture here of water on a sidewalk. I don't know if this is at UCLA. It looks like deferred maintenance. In one polarization, where we're looking at the polarization horizontal to the surface here, I'm seeing a lot of reflected skylight. That's natural sunlight and light blue from the blue sky, and it's overwhelming my view of the sidewalk. I mean, I can almost not see the sidewalk through all of this glare. I might, be afraid that there's a hole in there if I step in there and sprain my ankle on the way to class, which would be tragic, except I'm not going to class because this is virtual. What if I look at exactly the same spot of pavement here, same view exactly, except I look with a vertical polarizer that only lets vertically polarized light in? Well, then there's basically almost no glare at all. I can actually see directly to the light here, and I can see, oh, that's safe. I can splash in that. Very good. So that is exact. You can see how these Polaroids are so highly effective. It's ideal for sunglasses. I wouldn't want any sunglasses that didn't have Polaroid filters in them. And obviously, if some bozo gives you a pair of sunglasses which has been reconfigured so that the lenses have been rotated 90 degrees, what would those be? Those would be anti-sunglasses that will increase the glare and you won't be able to see anything. How sick is that? A whole batch of sunglasses that are defective because they were rotated, all the lenses were turned 90 degrees. What a disaster. But of course, a good reputable company would never do a mistake like that. Now, earlier on in this course, I did make a kind of a snide comment about Polaroids. I said they're cheap and they're really the same in all good brands of sunglasses. And I said a kind of unkind thing. I said that if you buy fancy sunglasses, since it's the same basic physics, you are wasting your money. Well, since that comment, I don't want to go into details, but the Department of Physics has entered into a cooperative learning arrangement with a very reputable manufacturer of high-quality top-end sunglasses, which in no way is interfering with the content of this lecture. This is UCLA. This is a higher education institution. We do not endorse, obviously, anybody's products for money, but of course we do want to support education, obviously, and we'll take corporate donations for that. So I do want to correct something I said in my last lecture. Even though the physics is exactly the same and the polarizer is the same in all brands of current modern sunglasses, some obviously do look cooler here. And I got this picture because we have another lecture where we're going to learn a little more about the physics of soccer, and so who more appropriate than to see David Beckham, and you can kind of see which sunglasses he prefers. And it may be for physics reasons, but probably it's just because, let's face it, they look much cooler. That's all you need to know about polarization, including all you need to know about sunglasses. And so hopefully you'll be able to do all of the problems now that we're going to throw at you on the midterms and final. Good luck.